Hi, a very good day to you all, and welcome to another session of the virtual classes of Scientia. And I'm Shaba Subramanian signing in order to discuss the concepts of rotational mechanics along with you. So, I again welcome all of you to the session. In this session, we will have a good look about the sessions that we are going to see as well as what we have learned earlier. Like you can see on the board, it is a format of a flowchart. As I have written on the board, you can see that this is a translational flowchart. So my aim is to remind you about the translational motion that you have studied in the one-dimensional, motion along a straight line, and in the two-dimension, that is motion along a plane, and the Newton's laws of motion in the unit of Newton's laws of motion, and about work, energy, and power. These are the things that you have already done in the previous sessions of mechanics. And if you have got that kind of an idea, the study of rotational mechanics becomes very simple, because it is nothing but it is another view of translational mechanics. Once you have got a view of translational mechanics, the study of rotation becomes very, very simple. So we are going to make it very simple, as we know the translational motion in detail, I guess. So like all of you know, the analysis or the physical analysis or any experiment in physics is nothing but it is just an observation. It is always observation. If you have got the patience to observe, if you have got the ability or tactics to observe phenomena in detail, you can understand the entire physics of that. So the observation is nothing but it is based on what? It is based on time. So the first input parameter for us is nothing but it is time. Or we are going to see the changes. We know that time is ticking down always. So that keeps on changing. So what happens to this world or the physical world with respect to the time? That is what we are going to see. So suppose the time is changing. We can say that the time is changing from say t1 to t2. You represent it as what? You will represent it as delta t. That is a change, or we will call it as an interval. And at a particular time, suppose we know the position of the particle, or the first observation that we are making is the position of the particle, which is represented by the vector r. And this will be explained always for a particular particle or a system or any body. It can be the projectile that you have studied, or it can be a particle which is executing circular motion just like Earth, or the planets which is revolving around Earth, or it can be a car moving on the road, or it can be a rocket which is propelled, or it can be a bullet which is fired from a gun. So for all of that, we have to know the characteristic parameter, which is defining the particle, the mass. Or you always call the mass as what? Mass represents the amount of inertia content of a body. Or we can even call it the mass as what? It is the translational inertia of the body. It's a translational inertia of the object. So the inputs for the flow chart or the translational flow chart are the mass of the object and where it is, or the position of the object at a particular time. Now we are going to make the analysis. Suppose the time is changing from t1 to t2. If the position is changing, we will represent it as what? Delta r, or that we say that the particle got displaced from one position to another position, or this is known as the displacement of the object. That is r2 minus r1, we will represent it as delta r. So with time, the displacement happened from r1 to r2. It can be in any fashion. It can be in a uniform fashion, it can be non-uniform fashion. That depends on the motion. Now, I have drawn a timeline. I am representing everything with respect to the time or with respect to the change in time. So, suppose the displacement is measured with respect to the time. We can say that it is delta r divided by delta t, rate of change of position or displacement divided by time taken. This gives the velocity of the particle. This gives the velocity of the object or the particle. So, connecting the displacement line with the time line, we got the velocity. Suppose the velocity is different at different time. That means from the starting time and the final time, the velocity is different. We know that the particle was not moving with uniformly, or it was not in a uniform motion, or the velocity was not uniform. In that case, we will say that the particle is getting accelerated, or it can be decelerated also, depending whether the velocity is increasing or decreasing. Now, if I connect that change of velocity with the time, or change of velocity with the change of time, I can represent that one as delta v divided by delta t, called as the acceleration of the particle. This is known as the acceleration of the particle. So, like all of you know that only this much is important to us when we are analyzing one-dimensional motion or one-dimensional kinematics or two-dimensional kinematics. Like the examples you have done, the free fall problem, projectile problem, circular motion. You must have used only these concepts. Till now, this parameter was silent. The mass was silent. Now I'm going to incorporate the mass into the flowchart. The mass, if I connect it with the velocity, what is this? This is the first parameter of what? Dynamics, we can say. Mass into velocity. Mass into velocity. What is mass into velocity? Mass into velocity represents momentum. Or we can say that represents the amount of motion content of an object, we can say. Or this is called as linear momentum of the particle. Linear momentum of the particle. Linear momentum. So linear momentum is the product of mass and velocity. And we have seen that the velocity was changing. The velocity was changing. If the velocity is changing, we can say that the momentum of the particle also will be changing. Because in all classical problems, we are treating that mass is constant. Or the problems which we are dealing, we are treating the mass is constant. So if the momentum is changing with time, I can connect the momentum line with the time line. The momentum line with the time line. I am connecting that to. Or what I am taking now is the change of momentum with time. Or I can write that one as delta p divided by delta t. Change of momentum with respect to time. This is nothing but this is your second law of motion, or this is Newton's second law of motion, which is the mathematical form of force acting. So force is defined as what? Force is defined as rate of change of linear momentum. And we have treated that the mass is constant, and if I make a small mathematical work over here, I'll get another connection. That is the connection between the mass and the acceleration. The mass and the acceleration. I'm not making that into contact with the other line. Put it in other ink. So this is giving you the most favorite equation, or the most simplest equation for the force, as mass into acceleration. So with this, we can say that we have seen the different concepts which we have studied in different units from 1D motion to the equations of motion, we can see, or to the Newton's laws of motion, we have seen in a single glance on the board. Now what are the products of these? So you can call this one as a flowchart. So we have to get a product from the flowchart or an output from the flowchart. The outputs of these are three eggs. The first egg is nothing but, that is a work done. Second egg is nothing but, that is energy. And the third egg is nothing but, that's a power delivered. What is the work done? We know the work done is F dot displacement, or force into displacement. And what is energy? Energy can be expressed as the amount of work done. Or this have got two forms. The one is kinetic, which is half mv square. Second is potential. That varies from gravitation into, it will be mgh form or g m1 m2 by r, or to the electrostatics it is different form. So that depends on the field in which the particle is. So the energy can be kinetic or it can be the potential. And what is power? Power is work done per unit time. What is work done? F dot S by T. What is S by T? S by T is velocity, or I can put it as F dot V. So look at the board, my students, and this makes a very simple way to understand all the concepts of mechanics in a single shot, or in a single screenshot. We can see all the aspects of kinematics and mechanics on a single screenshot. So that is all about the translation, or that is all about the translational motion or translation mechanics. Now, what if we move into the rotation? What happens when we move into the case of rotational mechanics? Now, just have a look on the board and try to understand it as much as possible by you. So as I said, if you have got this idea in your mind, the next will be very easy for you. I am moving into the rotational flow chart, or to the rotational mechanics, or I can also call it as an angular mechanics, because in rotation you know that the change which is happening is for the angle. So you may call it as rotational mechanics or an angular mechanics. So what I suggest you is, before going into the concepts or the derivations of any, try to have the flowchart which I am giving to you, so that the study, when you read the textbook or refer any material, it will be very easy for you. So I am going to make an analogous flowchart for rotational motion or rotational flowchart. So in rotation, we know that the time remains the same as the time itself in any mechanics. And in rotation, the position will be expressed by not simple position. This is called as an angular position. This is known as an angular position. Like you have seen in the case of circular motion when I was doing, it will be represented with two parameters. One is the radius parameter, the other one is angle made by the radius parameter. That is also a vector, which is a polar vector, an axial vector we can say. And that has got a perpendicular direction from the plane of that rotation that you have seen in circular motion. So when this position changes, what happens for, we will call it as an angular displacement. The displacement in rotation is called as angular displacement. The particle, when it is executing a rotation or a circular motion, what happens with that? It is making an angular displacement, and the angular displacement is represented with, so the change is happening for angle, So the angular displacement is nothing but it is delta theta. Now it is our time to measure the displacement, angular displacement with respect to the time. That is nothing but, that gives you the concept of angular velocity. What is angular velocity? Similar. Instead of delta r, it becomes delta theta. And the symbol is slightly different. The symbol for angular displacement, angular velocity is omega. Omega vector. Now what about acceleration? When the angular velocity is constant, we know that it is a uniform circular motion. When the angular velocity is changing, it is a non-uniform circular motion, or we can say that the particle is accelerated in the angular or along the periphery, or it is accelerated with respect to the time the velocity is changing. We will say that it is not delta v divided by delta t, it is delta omega divided by delta t. Acceleration is called as angular acceleration, represented by the symbol alpha vector. So see, the concepts is very simple because you don't have to study anything new, but you have to represent it in a new parameter manner, or you have to represent it in the terms of new parameter. You have to use new symbols, that's all. So if that is the case, now we should have corresponding quantities for momentum, corresponding quantities for force, as well as corresponding quantities for mass. So what is representing mass in rotational mechanics? We call the mass in translational mechanics as the translational inertia. So in rotation, the analogous quantity will be rotational inertia. Rotational inertia, or that is also called as what? Moment of inertia. That is known as moment of inertia. Moment of inertia. There is nothing new. Initially here there was inertia. I have taken moment of the inertia, and that is represented by a symbol I. That is represented by a symbol I. And in due course, when I am discussing that, you will see that this will be equal to sigma I 1 to n mi ri square, where mi's are different particles in the system and ri are the corresponding distances to that particle from the axis of rotation. If a body is rotating about an axis, the distance to individual particles. We will see the details while I am deriving that. So I have got the corresponding quantity for mass. So correspondingly I have to get what? I have to get momentum. Momentum, earlier it was mass into velocity. So here this momentum will be, here I have got moment of inertia. So this momentum also should be equal to moment of momentum. Moment of linear momentum. Moment of linear momentum is called as angular momentum. Moment of linear momentum is called as angular momentum. What is moment means? Moment is a cross product. So R cross P will give you the angular momentum represented by L, and that also can be written as the same form of mass into velocity. Instead of mass, it is I. Instead of velocity, it is angular velocity. So that can also be written in this form. So what about the force? We have force is equal to the rate of change of linear momentum with respect to time, delta P divided by delta T. So here also that should repeat. So delta P divided by delta T becomes what? Delta L divided by delta T, delta L divided by delta T. What is that? Here this is moment of momentum, this is moment of inertia, so this should be moment of force. Moment of force, or we call that one as what? We call that one as the torque. We call that one as the torque acting. This is the symbol tau. Moment of force means cross product of R and F. So as we have F is equal to ma, I am expecting instead of mi, instead of a alpha. So this can also be written as I into alpha. So tau can also be written in which form? I into alpha. So look it again. You can see everything over here are represented with what? Angular terms. Position is angular position. Displacement, angular displacement. Velocity, acceleration. Inertia replaced by moment of inertia. Momentum replaced by moment of momentum, which is R cross momentum, or it is I into omega. Force is replaced by moment of force, or that is called as the torque. This is called as what? This is called as the torque. This is called as the torque, represented as R cross F, or like M into A, this is I into alpha. So everything got replicated. This is a duplicative view of which one? Translation. So the rotation is duplicated version of translation mechanics. What about the outputs? Whether they will change? No. Here also the work done. Here it was work done was F dot S. Here the work done will become, instead of F it is tau dot S is delta theta. What about energy? It still will be having potential energy. Kinetic energy will change, as this is half mv square. Instead of m I am writing I, and instead of v I am writing omega, and this is kinetic energy of rotation. So I got the kinetic energy of which one? Rotational motion. What about the power? Power is still defined as work done per unit time. Work done here is tau into delta theta. So F into S can be written as tau dot delta theta. This is tau dot delta theta. What about delta theta divided by delta t? Delta theta divided by delta t is omega. So this becomes, instead of F dot V, this becomes tau dot omega. Yes. So we have got the complete parameters of translation motion, or we call this one as what? A rotational flowchart. So here we have all the parameters on the board. So like I said, for the translation, make a screenshot of this one and keep this one in your mind before you start rotational dynamics studies, because this makes a very simple approach to the entire unit. Now, in order to start with the parameters, I suggest you to see, in translation you must have studied from top to bottom. You study position, you study your displacement, you study velocity, acceleration, like this. But here, what I will suggest you is to start from this point. Start from the torque, go to the momentum, then go to the moment of inertia. Because all these you already will be knowing, because you have studied the circulation or circular motion. So our way of approach to the unit is, I am starting from the torque. What is torque? Why this is called as moment of force, or why this is considered as a force which is making rotation, or why this is an analogous quantity of force. And the next one is angular momentum. Why this is analogous to linear momentum, or that is similar to linear momentum in translation. And next is moment of inertia. Why this is treated as what? The analogous quantity of mass in rotation. And also we will be seeing this form, kinetic energy, which is considered as, or rotational kinetic energy, which is analogous to the translational kinetic energy. So like I used to say, take a snapshot, keep this one in your mind. Always this should be there when you are entering into the unit. So this is a simple making of the rotational flowchart. Now we are going to start with the concept of torque. What is torque? Why this is analogous to the force? How it can make a rotation or how it can create a rotation. Okay, we are going to study the aspect of torque. So now we are into the rotation or rotational dynamics, and the first thing that we are going to learn is a torque, which is termed as a quantity which is analogous to making a motion in rotation. This will be very easy to understand if you can consider an example of a linear body which is placed like this. And we will extend this example to other conditions also. First, I will start from the basic thing, which is a linear or just like a stick, a meter stick or a ruler or a wooden piece, anything. And suppose I am applying two forces, and suppose the length of this one is equal to R. I am applying a force over here, F at one end to the right, and another force at this end like this. Two forces are acting on the body, one on the top end and one on the bottom end. One is acting like this and the other one is acting like this. Now what will happen for this? Imagine I have got my pen over here. I am applying a force on this end and another force on this end. What will be happening? This body, let us look at the condition. Let us see what is the net force acting on the body. The net force acting on the body is one to the right and the other one to the left. F minus F, this is equal to 0. That means there is no translational force acting on the object. That means the body is not moving forward or now moving backward. But what will happen for this? If this kind of forces are acting on this, one is towards right and one is towards left, what will happen? This object will rotate with respect to the center. The object will rotate with respect to the center. So this creates what? We can see that two forces acting with equal magnitudes in the opposite direction on a body can create what? This can be called as a couple of forces. This is called as couple of forces. What is the effect of a couple? Look at the effect of the couple. This will rotate in this fashion and this end will rotate in this fashion. So we can see that a couple leads to the formation of a rotation, or a couple rotates the body. The effect or the couple rotates the body. So we can see that a torque is produced or a rotation is produced with the help of what? A couple. The magnitude of the couple or the amount of couple is measured as moment of the force. Moment of force. How we can measure the moment of force? Let us extend the direction of this force, and this is in this direction. So one force is over this line, another force is over this line. What is the distance between the two forces? Or I am asking you, what is the minimum distance between the two forces? Minimum distance is a perpendicular distance, right? Minimum distance will be the perpendicular distance. What's the perpendicular distance? R is the perpendicular distance. So we can say in this case that one of the force multiplied by the minimum distance will give you the moment of the force. In order to understand this concept mathematically much more clearly, I am making another diagram. Suppose the object was kept like this at a particular angle, and one force is acting over here, F, another force is acting over here. In this case also what will happen? This object will rotate like this. Here we can say that this body is making an angle theta, or R is making an angle theta with force. Extending this direction, I can say this is also making what? Angle theta. This F is also making angle theta. What is the perpendicular distance between the two? This is the perpendicular distance between the two forces. If R is the hypotenuse, opposite side will be nothing but that is R sine theta. So in general, in this case it is very simple because both of them are perpendicular, the angle was 90 degree, correct? Here this is an arbitrary case or a general case or a theta valued case. So what is the moment of a force? Moment of a force is perpendicular distance between the two, which is R sine theta times F, or I may write it as RF sine theta. RF sine theta. Moment of a force is called as the torque, or that is represented by the symbol tau. So what is tau? Tau is RF sine theta. R is a vector, F is a vector, theta is the angle between the two vectors, and here there is sine theta. You must be remembering AB sine theta. What is AB sine theta? That is A cross B. That's a cross product of two vectors. So this can be written as what? R cross F. So that is the expression for the torque. Torque is nothing but it is a cross product of position and the force, or that is the force multiplied by the perpendicular distance between the two. Now we can have different cases, we can see different cases. Suppose theta is equal to 0 degree. Theta is equal to 0 degree. What is theta equal to 0 degree? That is, force is acting in this direction and the part on the object is like this, R, and another force is acting like this. We can see R and F are making 0 degree, or with other one it is making 180 degree. We'll take 0 degree. If theta is 0 degree, first case is theta equal to 0 degree, sine theta equal to 0. In that case, what will be the torque? Torque is 0. That means by pushing a body along the line of the body, we can never rotate the body. So in order to rotate the body, there should be an inclination of angle between the length of the object and the force acting. The next case was this one which I was discussing, second case, when theta equal to 0. Here what is the peculiarity? This theta is 90 degree. If theta is 90 degree. If theta is 90 degree, what will be the tau value? Tau is R of sine theta. Sine theta for this case is maximum, which is 1, or that gives RF. So the torque is maximum when the body is placed, say like this, and a force is acting on it. That means the length of the object is like this, and this is the action of the force. So you can see the different cases in which we have got the value of the torque. So that is nothing but torque is defined as R cross F, or that is RF sine theta. This is easy to understand for this case. Now I will explain one more case for you. This is a general case. I have kept a body with length L like this. Suppose we have, or we are looking onto the action of a door, or a door is kept open like this, and this is the wall, or this is the wall onto which it is fixed. And we can say this point is hinged onto the wall. This is the wall, or this area is hinged onto the wall. Now suppose I apply force on this body, or I push the door like this. I can push it in any manner. I can push it perpendicularly, I can push it in a particular angle, or any manner. I am pushing it in applying a force onto it like this to the one end of the door onto this end. If I push the door, generally if the door is fixed firmly onto that, it will never fall down. Why that is not falling down? I have applied a force here. What is happening at the hinges? The hinge is applying a force in the backward direction. If this force is equal to this force, the wall will never fall down. Or we can say that these two constitutes a couple. That means if a door is fixed over here and I am applying a force over here, this part is not moving because the reaction of the hinge cancels the translational force. But what happens for the door? The door rotates. The door is rotating. So if the distance from this can be called as the axis of rotation. The distance to this point, let it be equal to r. If r is like this and if f is like this, if they are making angle theta, this is r and this is f, we can say the torque acting is still equal to r of sine theta. So even when one force is given, because in many problems we will not be having two forces as in general, it will not be directly given, but you have to guess. If one force is acting at one end of the body, the other end is fixed. Other end is fixed means other end is cancelling the applied force. So you can apply that one into the case of which one? Problems of doors or problems of particles fixed at one end. So that is a way in art to get the mathematical form of torque. We have got torque is equal to r cross f, or that is rf sine theta. R cross f or rf sine theta. Torque is represented as moment of the force, or rf sine theta. Now